At first glance, some discoveries seem almost insignificant, a slight dip in a star's brightness, a faint spectral fingerprint, a whisper of gas brushing against a detector. Yet every so often, the cosmos delivers something that halts the scientific world mid-breath, a signal that forces us to consider a stunning possibility that we may no longer be searching for life but observing it. Just 40 light years away, circling a cold and ancient red dwarf scarcely larger than Jupiter, lies a world at the center of one of the most intense debates in modern astronomy. TRAPPIST-1e orbits within the habitable zone of TRAPPIST-1, a faint ember of a star. And now, thanks to the precision of the James Webb Space Telescope, its atmosphere has been examined layer by layer with unprecedented detail. What the data suggests is extraordinary. For the first time, we may be looking at a planet that holds all the essential ingredients for life, oceans possibly, spreading beneath alien skies, chemistry, unfolding in complex chains, a red sun, looming 4 times larger in its sky than ours appears from Earth, a world that might, in some form, be alive. Tonight, we explore why TRAPPIST-1e has captured the imagination of astronomers across the globe, how James Webb pushed to the edge of its limits to probe this distant atmosphere, and what the evidence truly means for life beyond our solar system. When scientists first focused their telescopes on the dim red glow of TRAPPIST-1, expectations were modest. An M8 class red dwarf radiating at barely 1/1800th the brightness of our sun, ancient and faint, hardly the centerpiece of cosmic drama, but hidden in its subtle light curves, was a discovery unlike any before. Tiny dips revealed planets transiting the star, not 1 or 2, but 7 rocky, Earth-sized worlds, each orbiting closer to their star than Mercury does to ours, each tidally locked, forever showing the same face to their sun. At first, many experts dismissed the system as hostile. Red dwarfs are known for violent flares and magnetic storms, capable of shredding atmospheres before life ever has a chance. Yet TRAPPIST-1e refused to be ruled out. It sits squarely in the middle of the star's habitable zone, receiving roughly 2/3 of the light Earth does, enough to sustain liquid water if a stable atmosphere exists. That single question, does it have an atmosphere, became the driving force behind one of the most ambitious exoplanet observation campaigns ever attempted, because TRAPPIST-1e is not merely another rocky planet. It may be the most promising Earth-like world ever found around another star. When observation time on James Webb was granted, the Dreams collaboration moved quickly. They aimed the most powerful space telescope ever built directly at TRAPPIST-1e. Their objective was bold yet simple: determine whether this distant world possesses an atmosphere at all. Using transmission spectroscopy, they measured how the planet's atmosphere, if present, absorbs tiny portions of starlight during transits around a sun-like star. This task would be nearly impossible, but TRAPPIST-1's faintness offered an advantage. A transiting planet blocks a larger fraction of its light, strengthening the signal. Webb's NIR spec instrument captured data across 4 separate transits. The early results ruled out several scenarios immediately. There is no thick, primordial hydrogen-helium envelope. Such a light atmosphere would have been stripped long ago, nor does the planet appear wrapped in a dense Venus-like carbon dioxide shroud. A thin, Mars-like remnant atmosphere was also eliminated. What remained was something far more intriguing: the possibility of an Earth-like atmosphere dominated by nitrogen, with smaller yet vital amounts of carbon dioxide, methane, or water vapor at roughly 1 bar of pressure, similar to Earth. Such an atmosphere could redistribute heat across the tidally locked world. Oceans might span beneath a sky permanently divided between daylight and darkness. This was when whispers began. Careful, cautious whispers. Perhaps this world is not merely habitable. Perhaps it is alive. Yet an atmosphere alone does not ensure life, because TRAPPIST-1e is almost certainly tidally locked. One hemisphere basks in eternal daylight, while the other lies in perpetual night. The critical question became whether the planet can transport heat efficiently, enough to prevent catastrophic freezing or overheating. If methane dominates, greenhouse effects could paradoxically cool the surface, limiting water to the dayside alone. Instead of a global ocean, there might be a hemispheric sea beneath a red-orange sky, a cradle for prebiotic chemistry. Some models suggest life might flourish along the terminator, the narrow band of eternal twilight separating day and night. In this stable ring, temperatures could remain tempered enough for liquid water. Others propose something more exotic, an icy volcanic world with a subsurface ocean like Europa or Enceladus. Hydrothermal vents beneath ice could nurture emerging organisms, just as some believe occurred on early Earth. In every scenario, the implications are profound. TRAPPIST-1e may not resemble Earth exactly. It may be stranger, alien, and more varied, yet still fully capable of sustaining life. The star itself presents both danger and necessity. TRAPPIST-1's flares eclipse anything our sun has produced. The historic Carrington event on Earth would be routine here, potentially occurring every 2 days. Such radiation could strip atmospheres, molecule by molecule. And yet, ultraviolet radiation is also critical in forming RNA building blocks. Without stellar violence, life as we know it might never begin. Today, TRAPPIST-1 is calmer than in its youth. If TRAPPIST-1e retained a magnetic field generated by molten iron core, enhanced by tidal heating, its atmosphere may have survived billions of years of storms. Tidal forces similar to those shaping Io could inject heat into the planet's interior. Estimates suggest tidal heating 24 times stronger than Earth's, enough to fuel volcanism, maintain subsurface oceans, and recycle atmospheric gases. Internal heat could be the planet's hidden heartbeat. James Webb's findings are tantalizing, but not final. 15 additional transits are scheduled, each one lowering the noise floor and refining the spectral fingerprints of molecules. If consistent carbon dioxide, methane, nitrogen, or especially water vapor are confirmed, the implications will be historic. If the patterns align with a stable, Earth-like atmosphere, TRAPPIST-1e will become the strongest life candidate ever identified. But suspense remains. Will this planet reveal itself as a cold, airless marble, or as a living world beneath crimson skies? We may be months away from confirmation or heartbreak. Red dwarfs like TRAPPIST-1 burn slowly, living up to 10 trillion years, far longer than the universe's current age. Though their youth is violent, their maturity spans unimaginable time. If life emerged on TRAPPIST-1e, it could persist for billions upon billions of years, far longer than Earth will ever allow. Its greatest threat lies in its past. Its greatest gift lies in its future. Webb's early spectra reveal neither deep CO2 absorption nor unmistakable hydrogen signatures. Instead, there is ambiguity, a faint spectral silence. Either the planet is airless, or it possesses a compact atmosphere of heavier molecules that Webb is only just beginning to detect. This uncertainty is precisely what makes TRAPPIST-1e so compelling. A nitrogen-rich atmosphere like Earth's would leave only subtle fingerprints, requiring multiple observations to confirm. This is not a triumphant declaration. It is a scientific cliffhanger. The concept of Terminator habitability adds yet another layer of intrigue. A ring of perpetual dusk where winds circulate between hemispheres, creating a stable climate zone. Life there would evolve beneath. Permanent red twilight. Plants adapted to dim light. Organisms navigating gradients of temperature rather than day-night cycles. Perhaps not a global biosphere, but a thin ribbon of balance. Alternatively, life could survive beneath the surface entirely insulated from stellar fury. Subsurface oceans, shielded from flares and radiation, sustained by geothermal chemistry. Trappist, one may be habitable not because conditions are gentle, but because life learned to hide. In the end, Trappist, one stands as one of the most extraordinary discoveries in human history, not because it guarantees life, but because it refuses to let the question fade. For the first time, we are not gazing at distant gas giants or theoretical models. We are observing a rocky, Earth-sized world whose atmosphere may soon be confirmed within reach of our technology. A planet where chemistry could be unfolding right now. With 15 more James Webb transits on the horizon, the answer is approaching. Quietly, inevitably. Perhaps Trappist, one, will disappoint us. Perhaps it is barren and frozen. Or perhaps, for the first time in history, we will point to a distant star and say, there life exists. And when that moment comes, everything changes. Our science, our future, our understanding of ourselves. If you want to follow every update from James Webb, every atmospheric clue, and every breakthrough surrounding this remarkable world, stay with us, because we are closer than ever to answering humanity's oldest question, and the next piece of the truth could arrive at any moment. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.